Hello everyone, I hope you guys are doing extremely well. Today we are going to discuss another problem in our binary search tree series. The problem name is balance a binary search tree. So let's understand the problem description first. So we are given a binary search tree. Okay, now what do I mean by this? That means we are given the root node of a binary search tree and we want to return a balanced binary search tree. We want to return the root node of that balanced binary search tree with the same node values. That means the node values which are present in the initial binary search tree. Now what is a balanced binary search tree? A balanced binary search tree is nothing but if the depth of the two subtrees of every node differ by more than one, never differ by more than one. That means it is a balanced binary tree. Same, what is the definition of balanced binary tree? I have already explained you in the binary tree series. The same definition applies here. The same definition applies for balanced binary search trees as well. So for every node, the difference between the height of the left subtree and the height of the right subtree should be less than 1, less than or equal to 1. Okay, so if there is more than one answer, we can return any one of them. So let us carefully observe this problem using an example. Okay, so let's take an example. Let us say we are given the root node of the binary search tree as node 50. Now, the left child of node 15 is null and the right child of node 15 is, let's say, node 25. Now, for node 25, let us say the left child is null, but the right child is, let's say, node 35. Now, for node 35, let us say the left child is null, but the right child is node 45. So as we can clearly see, this tree is a binary search tree because for node 15 all the values in the left subtree, there are no values. All the values in the right subtree are greater than 15. 25, 35 and 45 are greater than 15. Similarly, for node 25 and 35 and 45, for node 25 there is no value in the left subtree, but the values in the right subtree are greater than it. For 35, the values in the right subtree are greater than 35, there is no value in the left subtree. But this is not a balanced binary search tree because for node 25, what is the height of left subtree? For node 25, the height of left subtree is nothing but 0. Now what is the height of right subtree? The height is nothing but 1, 2, 3. There are 3 nodes. So the height is 3. What is the height? I have already made a video on height of binary tree. Please check out that video. Okay, so the difference between them is 3 minus 0 is 3, which is greater than 1. That means this is not a balanced binary search tree. So what we want to do, we want to convert this binary search tree into a balanced binary search tree. So what will be the answer for this? So the answer for this will be 25 will be the root node. Okay, now for node 25, the left child will be node 15 and the right child will be node 35. Now for node 35, the left child will be null and the right child will be node 45. And now we have used the same values and we can observe here that for node 25, the values in the left subtree is 15. For node 15, there are no values in the left and right. So this is also obeying the binary search tree property. For node 35, there is no left subtree. For node 35, the right subtree is node 45 having a value greater than node 35. So this is also obeying the condition. For node 45, it is also obeying the binary search tree property. So the entire tree is a binary search tree. Fine. Now is this tree a balanced binary search tree? So for node 25, what is the left subtree height? So the height of left subtree is 1 because there is one node. Now how do we find height? I have already explained you. What is the height of right subtree for node 25? So the height is 1 and 2. So the difference between these two heights is 1, which is less than or equal to 1. For node 15, what is the height of left subtree? 0. What is the height of right subtree? 0. So the difference is 0, which is fine. Similarly, for node 35, what is the height of left subtree? The height of left subtree is 0. Okay, what is the height of right subtree? The height of right subtree is 1. The difference between these two is 1 minus 0 is 1. Fine, which is less than or equal to 1. For node 45, what is the height of left subtree? It is 0. What is the height of right subtree? So it is a 0. Now, okay, now what is the difference? The difference is 0. So it is also less than equal to 1. That means this binary search tree is a balanced binary search tree. So what we want to do, we want to return this node. We want to return this node 25. I hope the problem statement made sense to you guys now. Okay, so let us understand quickly that how we can solve this problem. So let's understand. So let's take a binary search tree. So let us say we are given the root node of the binary search tree as node 25. Now for node 25, the left child is, let's say, node 15 and the right child is node 35. Now for node 35, let us say the left child is nothing but node 32 and the right child is nothing but node 38. Now For node 38, let us say the left child is nothing but node 37 and the right child is nothing but node 40. Now, as we can clearly see, this is a binary search tree, but it is not a balanced binary search tree, because for node 25 the left subtree height is 1 and the right subtree height is 1, 2, 3 max depth. So 3 minus 1 is 2, which is greater than or equal to 1. That means this is not a balanced binary search tree. So how can we solve this problem? So the first step to solve this problem is to do an in-order traversal. Why we are doing an in-order traversal? Because the in-order traversal of the binary search tree is going to give me a sorted array, and once we have figured out a sorted array, we can always take the mid value of that array and we can construct the nodes using that values. So just bear with me and I'm going to explain what do I mean by this. So what will be the in-order traversal of this binary search tree? So the in-order traversal is nothing but processing the left subtree first and of a node, and then processing the node itself, and after that processing the right subtree. Okay, so now we are going to start with this root node. So root node is 25. Is there any left subtree for node 25? Yes, there is a left subtree for node 25. So we reach at node 15. I have already made a video on in-order traversal, so you guys can check it out. So for node 15, is there any left subtree? There is no left subtree. So fine, there is no left subtree. So now we are going to process the node. So we are going to add this value of node, that is 15, in my in-order array. Right. Okay, now is there any right subtree for node 15? There is no right subtree for node 15, so we simply gonna return. Now we'll reach at node 25. For node 25 we have processed the left subtree. Now we are processing the node, so we are going to add this value of node 25 in my in-order array, and now we are gonna process the right subtree. So the right subtree of node 25 is nothing but node 35, so we'll reach at node 35. Now for node 35 again, is there any left subtree? Yes, the left subtree of node 35 is nothing but node 32, so we'll reach at node 32. For node 32, is there any left subtree? There is no left subtree, so now we are going to process the node. So we are going to add the value of node 32 in my in-order array. Fine. Now is there any right subtree for node 32? There is no right subtree for node 32, so we're simply going to return from here. Now for node 35 we have processed the left subtree. Now we are going to process the node, so we are going to add this value of node 35 in my in-order array. Now what left to process? We are going to process the right subtree, so now we'll reach at node 38. Now for node 38 again, is there any left subtree? Yes, the left subtree of node 38 is node 37, so we'll reach at node 37. Now for node 37, is there any left subtree? There is no left subtree, so now we are going to process the node. So processing the node means adding the value of 37 in my in-order array. Fine. Now is there any right subtree? There is no right subtree for node 37, so we're simply going to return. Now for node 38 we have processed the entire left subtree. Now we are going to process the node, so adding the value of node 38 in my in-order array. Right. Now is there any right subtree for node 38? Yes, the right subtree of node 38 is node 40. So now for node 40, is there any left subtree? There is no left subtree. Now we are going to process the node. So processing the node, adding the value of node 40 in my in-order array. Now is there any right subtree for node 40? There is no right subtree for node 40, so we are simply going to return. Now for node 38 we have processed the entire left subtree, we have processed the node, we have processed the right subtree, so we can again return. Now for node 35 we have processed the entire left subtree, we have processed the node, we have processed the entire right subtree, so we can again return. Now for node 25 we have processed the entire left subtree, we have processed the node, and we have processed the entire right subtree, so we can again return. And in the end our in-order traversal will be stored in our array. Now once we have found out the in-order traversal, so as we can clearly see, this in-order traversal is in increasing order, because the in-order traversal of a binary search tree always gives us a sorted array. So now what we are going to do, we are going to use recursion to solve this problem. So how can we do that? We are always going to take the midpoint of the array, and after that we are going to divide that array in two consecutive halves. Firstly the left half, and secondly the right half. The left half is going to help us construct the left subtree of that node, and while the right half is going to help us construct the right subtree of that node. So let me explain what do I mean by this. So now what are the number of values present in this array? 1, 2, 3, 4, 5, 6, 7. So the size of the array is 7. That means the indexing will be 0, 1, 2, 3, 4, 5 and 6. Right. So initially our range will be from 0 to 6, the entire array. Right. Now 0 to 6, here we have low is not less than high. This will be our base case when our low will be greater than high. That means in that case we are out of the bounds of array. In that case we are simply going to return a null load, indicating that the subtree will be null. Now 0 to 6. So first of all, low is greater than high, fine. So now what we are going to do, we are going to find the mid value. So 0 plus 6 divided by 2 is 3. Okay, so we are going to construct a root node with the index 3. So index 3 is having a value 35. So we are going to construct a root node with value 35. Okay, now what will be the value of left subtree in this node 35? So the value of value in the left subtree will be nothing but the values present in the left half. So the left half values are 15, 25 and 32. So 15, 25 and then 32. And what is the right half? The right half is having value 37, 38 and 40. So 37, 38 and then 40. So from 0 to 6, what we have done, we have found the middle value. The mid value, we have constructed a node using that value, and after that we had made a call for the left child and we have made a call for the right child. So from 0 to 6, the left call gave us 0 to 2 because it will be from low comma mid minus 1, right? Because we have taken the mid to construct the root, and the high value will be from mid plus 1 to high. Fine. And this is what we are going to do for every node. Okay, so from 0 to 2, and then from here it will be nothing but 3 to, so we have taken the 3, so it will be nothing but 4 to 6. So our recursion has started from 0 to 6 and now it has reached to 0 to 2. Now for 0 to 2, again low is not greater than high. It is our base case. So if this base case is it, in that case we can just simply return. So from 0 to 2, again this is not the base case. So now what we need to do, we need to find the mid value. So what is the mid value? 0 plus 2 divided by 2 is nothing but 1. So now what we are going to do, we are going to construct a node with this index. So index is 25. Index is 1 and the value is 25. So what we are going to do, we are going to construct a node here. So node 25 will be constructed here. Fine. And now what is the left and what will be the right? So the left for 25 will be 15, which is left, and the right will be nothing but 32. So here if we take the left, what will be the left? It will be since we have taken 0, so it will be 0 0 and it will be nothing but 2 2. Okay, so for the left call, the indexes will range from low comma mid minus 1. Okay, and for the right call, it will range from mid plus 1 to high. So this is a rough idea of how we are going to solve this problem. So let us understand now more in more depth that how actually the recursion will work. So let's do that now. Okay, so I'm gonna start again. Yeah, okay, so let's say we are here. So initially our boundary was 0 to 6, right? 0 to 6. Okay, now for 0 to 6, the low is not greater than high. So the base case was if low is greater than high, in that case we just need to return null, right? So now for 0 to 6, what was the entire that present? The entire present was 15, 25, 32, 35, 37, 38, 40. Okay, so we are going to take the mid value. So 0 plus 6 by 2, so the mid value is 3, so the value will be 35. So what we are going to do, we are going to construct a node with this 35 value. So fine, we have constructed a node with this 35 value. Now what will be the left child for this node 35? The left child will come from 0 comma 2. How we have taken 0 comma 2? It is nothing but this left and then mid minus 1. How will the right child will come? The right child will come from 4 comma 6. So it will be the low value is replaced from mid plus 1 and the high is still the same. Fine, so our recursion has started from here and now it reached to here. Now for 0 comma 2, for 0 hyphen 2, so it is not again the base case. So what we are going to do, we are going to find the mid value. So the mid value is 0 plus 2 divided by 2, which is 1. So the mid value is this value, this one index. So what we are going to do, we are going to create a node with this value. So let's say we have created node 25 with this value. Now what is the left subtree of node 25? Obviously the left subtree will come from 0 comma mid minus 1. So it will be 0 0, and because mid minus 1, mid is 1, here the mid is 1, here the mid is 3. Also I'm writing the mid. Okay, so now mid, and the right will come from obviously mid plus 1 to high. So mid plus 1 is 1 plus 1 is 2, so 2 comma 2. Okay, so our recursion will reach here now. Now for 0 comma 0, it is not, low is not greater than high. So what we are going to do, we are going to find the mid value. So 0 plus 0 divided by 2, so it is nothing but 0. So the value is nothing but this. So what we are going to do, we are going to create a node with this value. So we can create a node with this value, so 15 will be created. Now what is the left child? So if we carefully observe, the left child will become 0, -1, which will be low is greater than high. That means it will simply return null from here. So I'm not writing it here. So from here we can just simply say that the 15's left child will be null, or we can also put one more base case. That base case can be if my mid value or if my low value is greater than equal to high. In that case I just need to return a node. So I don't make a call. So in that case I need to return a tree node, and that tree node will be nothing but the value of this. So it will be value, right? Okay, so we have returned from here. And now our recursion will reach at the right call. So here, so now for 2, 2, low is not greater than high, but low is equal to high. So what we are going to do, we are going to make a tree node. So tree node with this value is nothing but node 32. So let us make it value. So 32 will be made, and we are simply going to return from here and we are simply going to return this node from here. So our recursion will reach here. Now for node 25, we have created the left subtree, we have created the right subtree. So what we are going to do, we are going to return this node 25 to its upper function call. So node 25 will be returned here. Now for node 35, the left call has given us this entire subtree. Now we are going to process the right subtree call. So we'll reach at here. For 4, 6, low is not greater than high. Okay. So for 4, 6, okay, for 4, 6, low is not greater than high. So what we are going to do, we are going to find the mid value. So how can we find the mid value? 4 plus 6 divided by 2 is nothing but 5. Okay, so low is not equal to high. These two are not the base cases that we are getting here. We have find the mid value. So 5. So 5 is this value. So we are going to create a node with this value 38. So let's create a node with this value 38. And what will be the left child for node 38? So the left child will come from 4, and then mid -1 is 5 -1 is 4. And what will be the right child? The right child will be mid +1. 5 + 1 is 6, and high will still be 6. Right. So now our recursion will reach at this point. Now at this point, low is not greater than high, but low is equal to high. So what we are going to do, we are going to create a tree node with this index value. So 4, 4 value is 37. So we are going to create a tree node with this value. So let's create it. So 37 will be created, and we are simply going to return from here. So now we have returned from here, and our recursion will reach at right call. So for 6, 6, low is not greater than high, but low is equal to high. So what we are going to do, we are going to create a tree node with this 6th index value, so 40. So we are going to create a tree node with value 40, and now we are simply going to return this node. So now for node 38, we have got its left child covered, we have got its right child covered. So now we are going to return this node to its upper function call. So node 38 will be returned to its upper right call. Okay, fine, to its 0, 6 right call. Now for 0, 6, the left call has returned the entire left subtree, the right call has returned the entire right subtree. So now we are, what is this going to return? This is going to return its root node, and its root node is nothing but node 35. So we are going to, in the end, we are just going to get 35. 25 is the left child of 35, the right child is 38. Now for 25, the left child is 15 and the right child is 32. For 38, the left child is 37 and the right child is 40. And as you can clearly see, the height of this binary, this is a binary search tree, and it is also a balanced binary search tree. Now talking about the time complexity of this approach, since we are iterating the entire binary search tree and we are storing them in an array, it will take us big O of n, and after that we are processing every indexes, so it will again take big O of n. So the overall time complexity is nothing but big O of n, where n is the number of nodes present in this binary search tree. Now talking about the space complexity, the space complexity of this code is also big O of n. I hope the solution approach made sense to you guys. If you guys still have problems regarding the approach, don't worry, it will be clear once I will code it. So let's do the coding part. Okay, so now as you can clearly see, I have already declared a function called balance BST that is taking the root node as an argument. Root node is nothing but an object of class tree node. This tree node class is having a constructor that is initializing the value of the node. The left and the right child of any node is by default set as null. Now what is the first thing that we need to do? The first thing that we need to do is to store all of the values of this binary search tree in the form of an in-order array. So let's call an array as in-order array. Okay, and I am calling an in-order traversal function that is going to give me the in-order traversal of this binary search tree in the form of a list. So how can we find the in-order traversal? I have already explained you in previous videos. you can just check out those videos. So I just need to do, if the current node that I'm on is currently none, so in that case I just need to return an empty list. After that I need to make a call to the left child. So left answer is nothing but in order traversal root.left. After that I need to get my current answer, that is process the current node. So how can I process the node? I need to store this current node in some list. So current answer is equal to root.val. Okay, after this I need to make a call to the right answer. Okay, so current right answer is equal to in order traversal root.right. And then after this I just need to merge all these three answers. So left, return left answer. Don't forget to merge them in this order, because if you will not merge in this order then it is going to give you the wrong answer, because the correct answer for in order traversal is firstly get the left subtree answer, then process the current node, then process the right answer. So return left answer plus current answer plus right answer. So this is the in order traversal. Okay, now once we are done with the in order traversal, what we need to do, we need to create a recursive function. Okay, and in that recursive function the boundaries will be passed. So return, let's call it construct tree. Okay, so let's call that function as construct tree, and in that in order array will be passed. So initially the value of low will be the first index, that is the 0th index, and the value of high, that is the end index, will be nothing but length of in order -1. Okay, now whatever the answer this function will give, we are simply going to return that. So let's write this function now. So def construct tree. Okay, now we have in order array, we have left and we have right. Okay, or let's call them low and high. Okay, so low and high. So if my, first of all, what was the base case? If my low is greater than high, in that case I just need to return null. Okay, now what was my second base case? This base case is not necessary, but we have made this base case for a further optimization. So if my low is equal to high, in that case I need to return a tree node. So I need to return a tree node. Whatever the tree node value will have is nothing but in order of low. Okay, so the value present at the low index, I'm gonna make a tree node using that, and I'm going to return that tree node. Now if this is not the case, that means we need to find the mid. So how can I find the mid? I just need to do low plus high minus low by 2. Why I'm doing high minus low by 2? To avoid overflows. In Python we don't have overflows, but in other languages we have overflows. So low plus high minus low by 2 will help us to avoid overflow. Now once we have done this, we need to create a root with this value. So root is nothing but tree node, and then create a node with this value, so in order of mid. Okay, now what we need to do, we need to make a call for the left subtree. So root.left will be nothing but making a call to the left, so it will be in order. Low will still be the same, but high value will be decreased, so it will become mid -1, right, because the boundary has now changed. Now and for root.right, what will happen, it will be nothing but make a call to the right, and it will be in order. Now what will be the value for low? Low is nothing but mid +1, because we want higher values, and higher values will always come from mid +1, and then high will still be the same. And once we have got the answer for left and right and processed it, we just need to return this current root from here, and that's it. That's all about the code that we needed to do. So what we have done, we have firstly find the in order traversal of the given binary search tree, and we have got that in our in order array, and now we have created a function called construct tree. Construct tree is taking the in order, the low and the highest argument. Now we have discussed the two base cases. First of all, I have written down two base cases. Now after that, I have found the value of mid. Using that value of mid index, I have created the root node. Once I have created the root node, I have tried to find the left subtree of that root node and the right subtree. Now how I have tried to find the left subtree? The left subtree can be found with the left boundaries. What will be the left boundaries? It will be low comma mid -1, and the right subtree can be found with the right boundary. So right boundaries is nothing but mid +1 comma high, and in the end I just need to return root from here. And that's it. That's all about the code that I needed to do. I hope the code made sense to you guys. If you guys still have any queries regarding this problem, please drop your concern in the comment section, and I will be more than happy to help you. I am letting the code, I'm just giving the code you guys to run by yourself. Okay, regarding the series, I will be uploading more of the questions in the upcoming week, so keep following us. Until then, keep smiling and keep coding. Thank you.